Welcome to a screencast dealing with periodic properties of the elements. Chemists have known for quite a long time that there are lots of patterns or trends within the elements that make up our world. For example, lithium, sodium, potassium, rubidium, cesium. These are all metals that are soft, kind of shiny. They're very reactive. These are now called the alkali metals, and they react reasonably vigorously with water. Here's a picture of potassium being dropped in water, and it actually catches on fire. And when these metals react with water, they make a metal hydroxide. So, for example, potassium hydroxide, KOH, or lithium hydroxide, LiOH, and they make hydrogen gas. They also react with oxygen to make metal oxides that all have the formula M2O. So Li2O or K2O or Na2O. So these are a group of elements that have some properties in common, some trends, and also worth noting as we go from lithium to sodium to potassium, etc., they become increasingly reactive. The reactions are more and more vigorous. Now, this kind of periodic or repetitive behavior of the elements has been known for a long time, and a Russian chemist named Dmitry Mendeleev in about 1869, when he was working on writing a chemistry textbook while teaching at the University of St. Petersburg, he put the known elements on cards and arranged them according to both increasing weight of elements and also grouped them by properties. So this is kind of a simplified version, and he started with hydrogen, then lithium, beryllium, etc., going from top to bottom, left to right, as being shown here, in terms of increasing atomic mass, or mass of the elements. And then what he ended up doing was he would start a new row when there was an element of the next mass that had similar properties to something previous. For example, lithium and sodium have similar properties, so he aligned them in a column. And then magnesium and beryllium have similar properties, aluminum and boron, and so on. And then when he got to potassium, that was once again similar, this time to sodium and lithium, so it goes in the same column. A bunch of metals that are now known as transition metals had properties somewhat in common to each other. We'll kind of skip over those for now. And then he kept on going, and after those, the next known element was arsenic, which actually aligned pretty well with nitrogen and phosphorus in terms of its properties, and then selenium, etc. And there was a gap. There were no elements that were known to with appropriate increasing atomic masses that fit in with aluminum and silicon. And what Mendeleev did was not only made this arrangement of the elements, but he also predicted, and this was key, that there should be an element with a mass of about 70 that should have properties like aluminum, and there should be an element with mass maybe around 73 or so with properties like silicon, and he predicted those elements existed and we just hadn't found them yet. And it turned out, well, one thing is this was the first periodic table, and then the other thing was, not too long after this, the elements gallium and germanium were found in 1875 and 1886 respectively, and they were found to have properties very similar to what was predicted by Mendeleev in his periodic table. So this was a huge success in terms of explaining the arrangement of the elements, or at least organizing the arrangement of the elements. Now, Mendeleev's idea has been improved and refined a lot since 1869, but it's still a really big organizing principle in chemistry. But Mendeleev, although he came up with this idea, did not know why the periodic table had this particular structure. Well, we now know why the structure of the periodic table is the way it is, as predicted by Mendeleev and enhanced since then, and it's because of the arrangement of the electrons, or the specifically in terms of their energy levels and sublevels. And when we deal with electron configurations, you can kind of see how the periodic table's organization corresponds to the arrangement of the electrons in atoms. Now, there are a number of properties, and we're going to start with one known as, or basically dealing with size of atoms, atomic radius. There are a number of properties of the elements that are periodic and reflect the organization of the periodic table. And if you look at this listing of atomic radii, and these are done in units of picometers, which are 10 to the minus 12 meters, and you might notice that as you go across a row of the periodic table, the atomic sizes get gradually smaller. And as you go down a column of the periodic table, or a group, the atomic sizes get gradually bigger. And these are general trends. Atomic radius generally decreases going across a period and generally increases going down a group. Now, perhaps it's easier to see this trend if we do a graph of atomic radius versus atomic number. And you can see, if we start with the lightest element, hydrogen, the atomic radius of the next element, helium's a little smaller. Then the next element gets much, much bigger, and then gradually gets smaller, then much, much bigger, gradually smaller, etc. And also note, every time we go to much larger element, we've started a new row of the periodic table, or started a new shell that electrons are in. So these are first shell, second shell, third shell, starting the fourth shell, and so on. And then notice, of course, that the trend isn't perfect. For example, with the transition metals, these start going down, but then kind of go back up. And we're going to not worry about the details of, or the subtleties, I should say, of things like the transition metals. We're going to look more at the big trends like shown for the main group elements. Now, why does this happen? Why do we have these trends in size? And let's look at an example, the element sodium. It has an atomic radius of about 186 picometers, and it has 11 protons in the nucleus and 11 electrons in the electron energy levels. And here's our kind of cartoon version with 2 electrons in the first shell, 8 electrons in the second shell, and then 1 valence electron in the third shell. And if you let yourself kind of be the valence electron, what you'd note is you're going to feel an attraction to the nucleus, pretty strong attraction to that positive charge, but then you're going to be repelled by the nearby electrons, which also are negatively charged like you. So the balance of these attractions and repulsions is kind of a determiner of what's going on in the atom. Again, this is kind of a very simplified version. And roughly what we can do is say, well, we've got a first shell and a second shell of core electrons that there's 10 electrons inside of the valence electron for sodium, 10 electrons with surrounding, and we'll go back a second, surrounding 11 protons. Well, we have 11 positive charges, 10 negative charges. Effectively, that's kind of like having just one positive charge in the center of the atom, and that's what attracts the electron. This is called shielding of the nucleus. These core electrons shield the outer electrons from the full charge of the nucleus, and the effective nuclear charge is essentially the charge due to the combination of the charge of the nucleus and the charge of the surrounding core electrons. It's not exactly +1 in this case, but for our purposes, the basic idea of it's approximately +1 is sufficient for us. So you're a valence electron, and you feel something like a +1 charge pulling you towards the center of the atom or attracting you. Okay, what about the element magnesium? And notice with magnesium, we now have 12 protons in the nucleus and 2 valence electrons, but we still have 2 shells that are core electrons that are shielding, but same number of core electrons as with sodium. 10 electrons in the first and second shells, 12 protons in the nucleus. Very, very roughly speaking, that's like a +2 effective nuclear charge. And what we'd say is we have the same shielding of the nucleus as in sodium, but we have a larger number of protons in the nucleus, so it's a larger effective nuclear charge. And you might guess that if you have a larger effective nuclear charge, it pulls or attracts the electrons in the outer shell more, and therefore, even though there's 2 electrons in the outer shell, they're pulled inward enough that it has a smaller radius. Magnesium has a smaller radius than sodium. Now, this argument can be continued for the next elements in this row of the periodic table. Sodium, then magnesium, a little smaller, aluminum, 1 more proton, so even higher effective nuclear charge, then silicon, phosphorus, etc., gradually having larger and larger effective nuclear charge, roughly the same amount of shielding, and therefore getting smaller and smaller atomic radii. And in general, going across the row in the periodic table, the effective nuclear charge, we symbolize it by Z for charge and then EFF for effective, is increasing. We're in the same shell of electrons, so the radius decreases. And if you look at the other rows in the periodic table, that's roughly true as a trend, with some slight out of order values that we're not going to really worry about the subtleties. Now, what about if we go to a different row of the periodic table, in this case the element potassium? It has atomic number 19, so it has 19 protons and 19 electrons, and in this case it has a first energy level, a second energy level, and a third energy level that are core electrons, and then a fourth energy level that has 1 valence electron. So it has shielding as well, 1 more energy level worth of electrons shielding, but also a higher nuclear charge, and 19 protons surrounded by 18 core electrons. Once again, very, very roughly, is a +1 effective nuclear charge. And now if you're the valence electron, you're feeling a similar effective nuclear charge to the element sodium, but you're in the fourth energy level, not the third, so you're farther away from the nucleus. And what we would say is potassium has more or less the same shielding of the nucleus as sodium, but another energy level for the valence electron, which is farther away. Therefore, it has a larger nucleus than sodium. And then, of course, this same argument would continue if we went to the next element in that column, even farther out energy level, more shielding. If we went to a smaller or higher in the periodic table element like lithium, then we have similar shielding but 1 less shell. And so the general trend going down a column is to get increasingly large atoms because we go to more and more energy levels. So we could say that the effective nuclear charge is roughly the same, but we go to larger shells as we go down the column of the periodic table, so the radius of the atoms will increase. And if we look at other columns in the periodic table, we see similar trends. Okay, now another periodic property to look at is something called ionization energy. We've talked about this before or dealt with it before when dealing with the hydrogen atom. And first we're going to deal with what's called the first ionization energy. It's the energy needed to remove an atom, to remove an electron, in other words, to make an ion, removing an electron from an atom. And we can symbolize this by saying here's an atom, and specifically ionization energy is the energy needed to remove an electron from a gaseous atom. And when an electron's removed, we make a positive ion, an ion with a +1 charge, and the electron's been pulled off of the atom. Simple example is hydrogen. There's the nucleus, there's the electron. If we add enough energy, we can remove the electron from the atom, and what we're left with in this case is a hydrogen ion, which is just the nucleus, and an electron has been separated from that. And as has been seen before with analysis of hydrogen, the ionization energy, so IE here is going to stand for ionization energy, is 2.18 times 10 to the minus 18th joules to ionize 1 atom of hydrogen, and that works out to be about 1,316 kilojoules to ionize a mole of hydrogen. Here is a chart of first ionization energies for many of the elements in the periodic table, and if you look closely, perhaps you can detect some trends as you go either across a row of the periodic table or down a column, so going across a period or down a group. And perhaps you see some trends, but maybe it's easier to see the trends if we look at a graph of atomic number versus ionization energy. And if you do, now the trends are pretty obvious, somewhat like we had with atomic size or atomic radius versus atomic number. We get big increases followed by big decreases and sort of this gradual repetitive nature. And to take a look at what's going on and try to understand it, let's zoom in a bit to look at maybe the trend in ionization energy for just the first 20 elements. And notice if we start with hydrogen and then move to helium, big increase in ionization energy, and this is going across a row or across a period of the periodic table. Then when we go to lithium, which starts the next row, we have a big decrease in ionization energy, and then as we move across the row up to neon, which ends the second period of the periodic table, we have a gradual increase in ionization energy, and then when we start the next row, the third period with sodium, big drop, followed by gradual increase, followed by big drop to the fourth period, and so on. So in general, ionization energy increases going across a period and decreases going down a group. And if we look at the whole periodic table and look at the values, we see this is generally true. Ionization energy mostly increases going across a row, mostly decreases going down a group. So let's look at the factors that affect ionization energy. And what's going to make ionization energy larger? Well, if the nucleus has a larger charge, that's going to pull on electrons more, have a larger attractive force, so larger nuclear charge tends to correspond to larger ionization energy. If the outer electrons are closer in, then the force of attraction between the positive nucleus and the negative electrons is larger. And then if there's not much shielding between the nucleus and the electrons, then that's going to make the ionization energy larger as well. And remember, large ionization energy means it takes more energy to remove an electron. What'll make ionization energy smaller is pretty much the opposite of that. If we have a smaller nuclear charge, that's going to make it easier to remove electrons, less energy required, lower ionization energy. If we have farther away outer electrons, they're going to be easier to remove because there's less attractive force. And if we have more shielding, then that's going to reduce the effective nuclear charge, and that will make electrons easier to remove as well. Now, this can be applied to some chemical analysis of reactivity. For example, let's consider 3 alkali metals, lithium, sodium, potassium. They become increasingly reactive. We know this by trying the reactions and see how vigorous they are. They become increasingly reactive going down the periodic table. Lithium reacts with water, produces bubbles. Sodium reacts with water much more vigorously. And potassium, even a small chunk thrown in water, will tend to burst into flames. And the reason for this increase in reactivity has to do with the fact that as we go from lithium to sodium to potassium, the outer or valence electron is in an increasingly far away shell from the nucleus. It's well shielded, and so the electron is more easily removed as we go down the periodic table, and more easily removed electron corresponds to an more easily reaction. So we have increasing reactivity of alkali metals going down the periodic table. Now, at the other side of the periodic table, iodine, bromine, and chlorine, how they react is not by losing electrons, but by gaining electrons. So they like to form the negative charged ion. And as we go up the periodic table, we have similar shielding for the valence electrons in chlorine, bromine, and iodine. But what happens is that the electrons in chlorine are much closer to the nucleus than the electrons in bromine, and the electrons in iodine are even farther away. And because the electrons are going to be closer to the nucleus, then an electron is held more tightly if it's in a closer in energy shell, and so the halogens become more reactive going up the periodic table, because how they react is by gaining electrons, which is the opposite of what the alkali metals do. So thinking in terms of trends in ionization energy can help us understand chemical reactivity as well. Now, to form a magnesium ion, normally what we'd say is magnesium is going to tend to form the Mg+2 ion by having 2 electrons removed from it, and magnesium has the condensed electron configuration of a neon core and then 3s2, so 2 valence electrons in the 3s subshell, and if those are removed, magnesium's left with a neon noble gas core of electrons, and that's a pretty stable arrangement. But magnesium can actually form other ions. It can have multiple ions that are possible, and we can make an Mg+1 ion by removing 1 electron, and that requires about 738 kilojoules per mole. Now, to make an Mg+2 ion from an Mg+1 ion requires an additional 1451 kilojoules per mole. Takes a little more energy to remove the second electron from that shell. It's a little bit more tightly held than having 2 electrons being held by the nuclear charge, or the effective nuclear charge. But now notice, after 2 electrons have removed and we have a neon noble gas core of electrons, now we have to remove electrons from the second energy level, which is closer in. And it might not be surprising to think that forming the Mg3+ ion requires a lot more energy. So big jump in energy. Instead of going up by a factor of maybe 2 in terms of how much energy was needed to go from the first ionization energy to the second, it's now about a factor of 5 increase. Very big increase. And then to go from +3 to +4 requires even more energy, quite a bit more, but not as big a percent or fractional increase. Now it's only about 50% more energy to remove the 4th electron. Now, these are what are known as higher ionization energies, and for magnesium, the higher ionization energies, so first ionization energy, second, third, fourth, etc., correspond to removing the first electron, the second electron, the third electron, and so on. Notice what happens. Ionization energies increase the more electrons you remove, but there's a really big jump going from the third energy level, removing electrons, to the second energy level, removing electrons. And if we look at higher ionization energies for other elements, and now we'll do the elements in the third row of the periodic table, notice that this basic principle still applies. For sodium, removing 1 electron takes 496 kilojoules per mole. The second electron is going to now come from the inner shell, from the second energy level, and there's a huge percent increase in energy required, and then energy required for subsequent electrons continues to go up, but not by as big a fraction. For aluminum, first electron, second electron, third electron take increasing amounts of energy to remove, but then the fourth electron removed from aluminum, now we have to remove a second shell instead of a third shell electron, and there's a huge increase as we jump from one shell to the inner shell. Same thing for silicon, but now it takes 4 electrons removed before you remove one from the fifth electron gets removed from the second shell, and so on. So higher ionization energies, the big thing to note is always increase in ionization energy for the next electron, and big jump in ionization energy for moving from one shell to the next. And then the last periodic property we'll look at is something called electron affinity. It's the energy change for an atom when it gains an electron to form a negative ion. So it's the affinity of an atom for electrons, and it's the energy for the process of a gaseous atom gaining electron to make a gaseous negative ion. And an example would be fluorine can gain an electron to make fluoride, and the electron affinity, EA here stands for electron affinity, is negative 322 kilojoules per mole. Now note, electron affinities are negative, and what that means is that energy is released when the electron is added to the atom. So this is an exothermic process. And what we will do with electron affinities is just simply note that there are some elements in the periodic table that have particularly negative electron affinities. These are atoms that are fairly fairly happy to, so to speak, gain an electron and make a negative ion. And the ones probably most worthy of note are things like the halogens and oxygen, things kind of in this corner of the periodic table. These are atoms that are reasonably happy to form negative charged ions, and electron affinity corresponds to gaining 1 electron. So that is it for what we'll do with electron affinity. And that's it for what we'll do with periodic properties.